People are remarkable in all sorts of ways, but our attention and short-term memory are limited resources. Fortunately, there's hope. The representations provided by language, gesture, drawings, and objects help us communicate and reason. And, importantly for design, different representations can facilitate or hinder different thoughts. The insight of today's lecture is the ways in which we in the world organize and represent ideas can have a drastic impact on our cognitive abilities, for better and for worse. Things can help us think, and you can leverage this as a designer. Let's start with an example that comes from Don Norman and Jiaji Zhang. There's a really strange diner, and in this diner, the waitstaff not so good, and the three people at the diner ordered oranges, but they ended up on the wrong plates. And your job, you can try this at home, is to help sort out which orange belongs on which plate. And so the way that the oranges puzzle works is you need to order the oranges by size, largest to smallest, left to right. Only one orange can be transferred at a time. An orange can only be transferred to a plate on which it'll be the largest, and only the largest orange on a plate can be transferred to another plate. And so I have 3 oranges here. Our recording got a little bit delayed because somebody ate this little orange, and so I had to go back to the market and get another one. But we have an orange now, and let me show you how this works. So I'm going to array these out. I have my diner coffee. Here you have the 3 oranges as delivered by the waitstaff, and you can see they're in the wrong order. The largest one's in the middle, and the middle one's over here, and the smallest one, which needs to be over here, is over on this side. And so to help save these diners, one of the TAs for the HCI Online class, Alex, is going to come and sort this out.
Oh man, this looks very difficult. So I have to only transfer 1 orange at a time, right?
1 orange at a time.
And it can only be to the biggest plate.
It has to be the largest orange on the plate.
Okay. So can I transfer this here?
No, because then it won't be the largest orange.
Okay. So can I transfer it here?
You bet.
Great. And then can I transfer this one over here?
Sure.
And then this one here?
You got it. Well done.
Thank you.
And there's a couple other diners who got similar orders. They all wanted bagels, and let's see. So they had a first course of oranges. The second course is going to be bagels. The real bagels puzzle is why can't you get a decent bagel in California? But the bagels puzzle that we have for today is a little bit different. So we have our largest bagel, medium bagel, smallest bagel. So the plan is the same, except with the bagels, you have the ability to stack them. You can put a larger bagel on top of a smaller bagel, but not a smaller bagel on top of a larger one. And so at any point in time, just like the oranges, it needs to be the largest one on the plate. And these are in reverse order, and Alex is going to help us again, rearranging the bagels so that the largest is on the left and the smallest is on the right.
Cool. So it has to be the largest, right?
Largest on the left.
So I can move this one here.
You got it.
And I can move this one here.
Yep.
And I can move this one here.
Yep.
Good.
There you go. Well done. Now all of our diners are happy. Presuming, of course, these were New York bagels, which they're not, but that's close enough for now. So that's our bagels game for today. You can try this at home, and what you see is that the fact that the bagels represents some of the constraints of the problem in the physical structure makes it much easier to remember the state. You don't have to remember which of these 2 bagels is larger and therefore movable, because the larger one is on top. You're not going to move this medium-sized bagel that's underneath. And that makes it a lot easier when the representation of the problem enforces the constraints and the rules of the problem. And you can think of this in a lot of ways, like when you leave your keys by the door, so that right as you walk out the door, you bring your keys with you. That's a way of structuring the physical world to serve as a reminder and to embed the constraints that you need to leave with your keys in the physical space itself. And as some of you may have realized, you can think of these as being Towers of Hanoi. And what's interesting about this Towers of Hanoi is the kids' game where you can move circles between pegs. They look a lot like bagels. And what we've done is we've turned this Towers of Hanoi game into something where the rules are the same. It's just the representation that's changed. And let's play a game. We're gonna play a card game now. 2 players. Each of you is going to draw a number one at a time, such that you have 3 numbers that add up to 15. And your draw is without replacement. So if I pick 5, that's no longer available. For example, if I was able to get 4, 5, and 6, together those add up to 15, and that would be a winning hand. So let's say, for example, I pick 5 for starters, and the other player picks 6. So I pick 3, and the other player picks 2. And then I pick 7. That would be a winning hand. And this is hard enough for one player. As you can see, it's even harder to try and play both sides. So we can make this a little bit easier. So let's say instead of having it be numbers imaginary in our head, we'll do the same thing, but with playing cards. And so I'm going to be able to have the numbers 1 through 9 here, or ace through 9. So here we have the playing cards, ace through 9. And again, 2 players. And this time we can lay them out on the table. So I'll lay these out so I can see them. And again, I'll start out by picking 5. And the other player might pick 6. And so I'll go 3. And at this point, especially if the other player can see my numbers, they'll know that 7 is what I want next. So they're going to go 7. And I'll go 2 to prevent their 15. And all right, now they got to head off on another attack. So maybe we can do... Let's try this 1. I haven't thought it through, but that might help. And at this point, you start to wonder whether this is going to work. So I'll take. I'm not really playing here, but I'll take 9, 12, 14, almost, and there's kind of nothing you can do at this point, and so no dice. A lot easier, especially early on, but still somewhat challenging. Let's play another game. We'll pick an easier one this time. How about tic-tac-toe? So this is pretty easy. I think many of you know this game. So we can do X's and O's. Somebody can go X, and somebody can go O. We can do X and O, and X and O, and X wins. That game is a whole lot faster than either of the 2 cards we played. But what might shock you is that these 2 games are isomorphs. So I can fill in the numbers 1 through 9 and have them be exactly equivalent to our card game. Any row or diagonal that adds to 15 also produces a winning game in tic-tac-toe. So for example, I can pick this right column. That's 15, 15, all the way through. And what we see from this is that the way that you represent the problem, drawing numbers in our head, cards on the table, or numbers in a grid, has drastic influences on our ability to solve that problem fluently and to see alternate solutions and to be able to coordinate our action with another person. And this is why Herb Simon, the famous artificial intelligence and cognitive science researcher, writes that solving a problem simply means representing it so as to make the solution transparent. For example, if you think about proofs in mathematics, what's true at the end of the proof is also true at the beginning. The only thing that's changed along the way is that the fact that the proof is indeed true has been rendered clear to the reader. Why were the oranges puzzle and the number selection game so difficult? It's because both of them taxed our working memory. We had to keep in mind what moves were possible, what numbers we held, what the other person was thinking and maybe doing. And that was a lot to keep in mind all at once. Human beings are incredible in all sorts of ways. Working memory is not one of them. And one of the most important things that we can do with user interfaces, by embedding the constraints of the problem in the user interface itself, is to offload working memory so that those limited resources become available for other people. You may have heard the famous 7 plus or minus 2 as the limit of working memory, that we can keep 7 plus or minus 2 things available at any point in time. And that's not exactly true. The real story is a bit more complicated. But if you want to have a rule of thumb to work with as a designer, I suggest 2 plus or minus 2, that basically don't require users to keep anything in mind that you can possibly put on the screen. So far, the examples that we've looked at, oranges, bagels, cards, tic-tac-toe, are kind of toy problems. And they may make for some good entertainment at a dinner party, but it's not real-world stuff. They demonstrate, however, principles of the power of distributed cognition that absolutely have real-world impact. One great example of this is the task management system, Getting Things Done, is very much designed with the principles of distributed cognition in mind. So, for example, one of the rules of the Getting Things Done system is that whenever something comes to your mind that you need to do, the first thing you do is write it down somewhere, anywhere. And the reason for that is if you have something in mind that needs to be completed and you haven't written it down yet, you're spending a lot of cycles of working memory remembering I need to do my laundry this evening, I need to do my laundry, I need to do my laundry. And that's chewing up resources that could be better deployed elsewhere. Write it down, gets it out of your mind, and you can move on. One of the words that people toss around all the time in terms of effective user interfaces is that this user interface is natural. And when we say that, we mean a couple of different things. But one of the things that we mean, we can see in our example of the oranges and the bagels, that the bagels as a task is more natural because the properties of the representation bagels can stack matches the properties of the thing that's being represented. One of my favorite user interfaces for this perspective is the Proteus ingestible pill. This is a pill that when you swallow it, it sends out a little signal so that your phone or the internet knows that you've taken this pill. And the ability of keeping track of whether you've taken the pill or not automatically by virtue of taking the pill is a really natural user interface. The ingestion act serves both to take the pill and to mark that you have done so. There's another example of a really natural interaction in this system, which is that in addition to the pill, there's a transmitter that you need to stick to your body. And the transmitter has a limited battery life. So how do you turn the transmitter on? It's a Band-Aid-like system. And the way that you turn on the transmitter is you peel back the Band-Aid bandage, and that turns it on. And so again, that action that you need to do to stick it on yourself is exactly the same action that you use to turn the pill on. And so by integrating the necessary step with the step that's easy to forget, you don't forget the step anymore. So let's bring this back to normal user interfaces. Here's an example of the print dialog on a Macintosh. And one of the things that you can see here is that there's a world in miniature strategy in this print dialog box. So if I want to look at the Stanford Academic Calendar, I can print that here. And what we're going to look at is, here's our world in miniature, where we see the entire legal-sized page shown inside the dialog box. And one of the things that makes clear is that I'm not going to be able to fit the top and the bottom of the page on a letter-sized page, because a letter-sized page is 3 inches shorter than the legal page. And so consequently, it's probably not something I want to do. And one of the things that I like about this is that by showing you the world in miniature, the challenges of working that you've got to decide here become much clearer. Here's another example. This is from Microsoft Word, and what we can see here is I'm again about to print this, and the dialog box that I get from Word says a footer of section 1 is set outside the printable area of the page. Do you want to continue? And I can click yes, or I can click no. Now, in order to answer this problem, I need to know, is it just that the bounding box of the footer is outside what the printer can print, and so it's irrelevant? Or is there actually content that I need that won't be printed? None of that's available from this dialog box. And so unlike the previous print dialog where we saw the world in miniature and could see what was being cut off, here we have no idea what's being cut off, and consequently this is a much less effective user interface. And that's the end of part 1.